All right, welcome back, everyone. Today, we're taking a highly detailed, three-dimensional descent into the absolutely high-stakes world of oil and gas well engineering. It's pretty easy to look at a pump jack nodding away in a field and just think, well, that's all there is to it, right? But we're going to look way past the surface today. We want to understand exactly what happens literally miles deep underground to keep global energy flowing. So buckle up, because we're diving straight into the fascinating and honestly mostly hidden life cycle of well completions and workovers. Let's get into it.
So there's this really common misconception that once that massive drilling rig packs up and drives off the site, the job is pretty much done. But actually, a freshly drilled well is in absolutely no condition to produce hydrocarbons. What we have at that point is essentially just a raw, drilled hole. It's a highly volatile problem of immense pressure just waiting for an engineered solution. It's basically an open conduit to the Earth's extreme forces. So the big question we really need to ask is, how do we actually get those hydrocarbons safely to the surface without, a catastrophic failure?
Well, the answer lies in a process known in the industry as well completion. But hold on, before we even start shoving equipment into the ground, engineers have to do a really careful interpretation of well test data. They take physical rock samples, that's called coring, and they run sensors down the hole in a process called logging. Based on all that data, they have to make a definitive choice. Do we plug and abandon this well because it's just not commercially viable, or do we go ahead and complete it? Now, when we say completion, we actually mean two closely related things. First, it's the geometrical concept of how the well should be configured to best tap into the reservoir. And second, it's the actual physical downhole hardware that gets run into the wellbore to allow for that safe, controlled flow of petroleum. To really grasp this, let's anchor ourselves deep underground. Notice those geological layers descending. You've got the surface water zone, then the impermeable caprock, and finally the gas and oil zones way down at the bottom. The well itself is lined with different layers of heavy steel and cement. You have the conductor casing right at the very top, surface casing specifically designed to protect fresh groundwater, which is obviously absolutely crucial, and then intermediate casing going much deeper. And running right down the center of the whole shebang is the production tubing. This is the main artery of our well, and it can extend literally miles into the earth.
Now, you might be wondering, why do we even need that central artery? Well, let's talk about the stakes here. Down in those producing formations, we are dealing with immense formation pressure and highly corrosive fluids. To put that into perspective, we're talking about pressures that could easily crush a military submarine. No joke. Without a properly designed completion string, these intense underground forces would just wreak havoc. That extreme pressure could cause an uncontrolled blowout right at the surface. And those harsh, corrosive formation fluids would easily attack and destroy the outer production casing. So the completion hardware isn't just a bunch of pipes. It acts as our heavy-duty armor and our precision control mechanism.
Let's trace our chronological descent down the wellbore and see exactly how this system is built. It generally goes down in three critical steps. Step 1, we run in the production tubing string. Now, interestingly, these are often designed as tapered strings. Think of it kind of like a giant funnel. They have a smaller inside diameter at the bottom and a larger one at the top. This is done to optimize pressure drops and really maximize those production rates. Step 2, we install highly specific flow control devices all along that tubing as it goes down. And step 3, we land the tubing hanger at the surface, which is what physically suspends all that incredibly heavy steel tubing deep inside the well. This layout really brilliantly illustrates how those flow control devices are integrated into the system. All along that tubing string, you're going to find components called landing nipples, strategically placed. And you can think of these simply as engineered docking stations. They aren't just arbitrary joints, They're specifically machined profiles that allow engineers to do vital pressure testing during the installation phase. And even more importantly, these docking stations are where they locate other critical flow controls, pressure and temperature gauges, and those all-important downhole safety valves at their precise, appropriate depths within the well. It's essentially a massive modular system built for ultimate control.
But here's the thing. The tubing alone just isn't enough. We need a way to completely isolate the flow from the rest of the wellbore. And that brings us to what is arguably one of the most vital components in the entire well, the production packer. You can think of the packer as the ultimate annular seal. It actively seals off the annular space, which, by the way, is just the empty cylindrical gap between the outside of the production tubing and the inside of the casing. By forming this impenetrable barrier, the packer actually forces all the reservoir fluids to travel straight up through the tubing. This single component is a massive safeguard. It keeps dangerous well pressures and highly corrosive fluids from getting into the annulus, essentially preventing catastrophic environmental disasters, by maintaining the overall structural integrity of the well itself. So the crucial point we have to figure out is how on earth do we get this heavy-duty seal to lock tightly against the casing wall when it's miles underground? Well, engineers generally use three primary, very distinct methods to set permanent packers in place. First, they can be set using hydraulic pressure from the tubing, where intense differential fluid pressure is applied to literally expand the seal. Second, they can be set using a mechanical mechanism. This usually involves the physical downward movement and rotation of the tubing string itself to engage the packer. Or third, they can be set remotely using an electric wire line.
Now, the sheer ingenuity of this electric wireline setting tool is absolutely incredible. When exact depth placement is just absolutely critical, engineers will run this tool down on a specialized electric cable, constantly correlating its depth with previous well logs to make sure they're exactly where they need to be. Once they hit that exact target depth, an electrical signal is sent straight from the surface. And get this signal fires an explosive charge right at the top of the device. That controlled underground explosion drives down a piston, which in turn forces a central rod, called a setting mandrel, downward. This intense mechanical thrust expands the packer's rubber elements out tightly against the casing wall. Finally, once the packer is fully set, a perfectly calibrated release stud snaps under the tension, breaking the tool free so it can be pulled all the way back to the surface, leaving the packer permanently embedded. After all of that intricate downhole equipment is finally set, we arrive at the climax of our completion journey, right back at the surface. Here we have the tubing hanger, which, as we mentioned earlier, suspends the tubing and provides essential barrier protection. And capping off the entire system is the Christmas tree. This robust assembly of master valves and production wings is what finally gives operators complete surface control over those high-pressure fluids emerging from the earth. With this Christmas tree installed, the well is now fully completed and ready to be brought safely onto production. All right, let's fast forward a bit. We're going to execute a multi-year time jump here. The well has been producing perfectly for years, but as we all know, nothing lasts forever. So what happens when those downhole components inevitably fail, or the fundamental geological conditions of the underground reservoir begin to change? Well, this transitions us right out of the initial completion phase and into the heavy-duty maintenance phase, something known in the industry as a workover operation.
You see, even the absolute best engineered wells face extreme wear and tear, just given the incredibly harsh environments they operate in. A workover is basically triggered when the current completion becomes terminally unsuitable. This could be because the steel production tubing has become dangerously damaged by years of corrosion, which directly threatens the integrity of the whole well, or maybe complex moving downhole components, like those retrievable safety valves or large electrical submersible pumps, have simply malfunctioned and need to be physically replaced. Sometimes the hardware is actually perfectly fine, but changing reservoir conditions dictate that a brand new completion design is needed to handle entirely different production rates. In all of these cases, a massive workover rig has to return to the site to physically intervene.
A workover is a major, highly intensive operation. You are essentially dismantling the well to fix it. The chronological extraction process goes roughly like this. First, the wellhead and surface flow lines are completely removed to clear the way. Next, the tubing hanger is lifted from the casing head to start the arduous process of pulling the entire completion string out of the wellbore. But remember that permanent packer we explosively locked into the casing earlier? Yeah, it won't budge. It was designed specifically not to. Because it's permanent, engineers often have to cut the tubing just above it to pull the upper string out first. Then, they must literally drill and mill out the old packer from the casing wall to remove it. Milling is incredibly difficult because you're grinding through hardened steel and heavy-duty rubber miles underground with only a rotating bit. In fact, it's often so difficult that they simply leave the old packer in place, set a brand new packer right above it, and run new tubing down to reconnect. I mean, it is incredibly intense, heavy-duty engineering.
Which really brings us to our final thought for this explainer. Just look at the sheer scale and complexity of what we've covered today. From explosive setting tools deployed miles deep to massive surface tree assemblies containing extreme pressures. As global energy demands constantly shift, it really makes you wonder, how many of these complex underground infrastructures are silently being repaired, milled out, and entirely re-engineered beneath our feet right at this very moment? It's a vast, completely hidden life cycle of continuous, high-stakes engineering that literally keeps our modern world moving. Thank you so much for joining me on this explainer, and keep that curiosity focused and fired up.